So we're continuing on. I realize that there's a typo here. I guess this would be exercise 5, but there's a bunch of typos here. So don't worry about the exercise numbers, although I will be referencing exercise 1 here shortly. Just to give you a heads up, there's a lot of sequences out there, and one's called the Fibonacci sequence. And it can be very confusing because now you can see that they use n plus 1, they use n, and then they use n minus 1. So what it's saying is maybe I would use the phrase like the current term is this one, the previous term is the n minus 1 term, and then the next term would be like the n plus 1. So as you look closely at finding a sub 3, well, you might come up with your own equation that says, okay, well, let's let 3 equal n plus 1. So therefore, n must equal, if we subtract 1 over 2. And then from there you could say, okay, well, if 2 is equal to n, then n minus 1, 2 minus 1 is equal to 1. So what I'm saying is that if I want to find a sub 3, you take a sub 2, because n is 2, plus a sub 1. So I guess I'll switch back to blue, so a sub 3 would be equal to a sub 2, which is 1, plus a sub 1, which is equal to 1. So the third term in the sequence is 2. And after some practice, I think you'll notice the pattern. So the pattern goes 1, 1, and then the third term is 2. So if I went on to a sub 4, that's equal to I guess the current term is how I phrased it, plus the previous term. So what we're looking at there is the third term was 2. The second term, which we found earlier, was 1. So this would be 2 plus 1 equals 3. I don't know if you've seen the pattern yet, or if you've even heard of the Fibonacci sequence, but 1 plus 1 is 2, 1 plus 2 equals 3, 2 plus 3 equals 5, 3 plus 5 equals 8. I guess I could stop right there because that's the sixth term. But if you wanted to keep going just for practice, 5 plus 8 equals 13, 8 plus 13 equals 21, and this pattern goes on forever. 13 plus 21 is 34. But I guess if I had to put a box around everything, I would stop at 1, 2, 3, 4, 5, the sixth term. And this is the Fibonacci sequence. If anybody gets bored, you can feel free to Google the Fibonacci sequence. There's a lot of neat things in nature about this. There's actually word problems that are created to replicate Fibonacci and his sequence he came up with. But that's really all I want to talk about with this. So if you get bored, Google this. There's a lot of interesting information out there about the Fibonacci sequence, and it's defined recursively. So we can do as many recursive definitions as we wanted to. If I gave you the first 3 terms, I could come up with a new formula. All right, I think that's enough of that. So as I move on to the next exercise, again, I do realize that these are numbered incorrectly. You don't have to tell me that. This time in exercise 4, they do not want the recursive definition. They want you to create an equation based off of a formula. Right now, I'm not going to give you any special formula. I just want you to play around with numbers, see if you can guess and check, and see if you get something. And along the way, I will try to give you some advice. And my advice is based off of, is there a common difference? Question mark. Or is there a common ratio? Question mark. And in letter A here, there's definitely a common difference that we're going up by 1. So for right now, instead of giving you a formula, I'm just going to tell you that treat a problem that has a common difference as if it's a linear problem. So again, I'm going to practice the formula as if it's a function, and the common difference going up by 1 in this problem, that's kind of like the slope in a problem. So it's 1n. Let me make that look like a 1 instead of natural log. So 1, because that's the difference, times n. But the thing is if I plugged in 1 in for n right now, I wouldn't start at 4. I would be at 1. So what could I add to 1 to get up to 4? Well, I could add 3 to it. Now, just as a heads up, it's okay if you want to rewrite it as subscript, and if you wanted to drop that n, you could just write the problem like this. I'm just giving you some different options on what a correct answer is. And when we get to a later unit, I will show you a formula that always works to come up with these answers. But right now, I want you to play around and see if you can figure things out in your head, because I think you can learn more that way. And you can double check that this is right. Is the first term, plugging 1 in for n plus 3 equal to 4, the first term? Yeah. What about plugging in 2? Does 2 plus 3 give me 5? Yeah, that's the second term. Is 3 in for n plus 3 equal to 6? Yeah. So, yeah, it's a lot of guessing and checking. Okay, I'm okay if you struggle through this. I will eventually get you to a formula. I just want you to kind of play around. So if you notice when I talked about the difference being a linear function, well, a common ratio turns into an exponential function. And usually what the common ratio is, in this case, the common ratio is 2. It actually is really easy because it starts with 2 and it's going by 2. So this one's actually pretty straightforward, that if you write it as 2 to the nth power gives you the correct answer. Again, I will show you a method that is always working. If you Google the method, I'm sure you could figure it out if you read a few articles. But what I'm saying is, if you plug in 1 in for n, is it true that 2 to the first power gives you the first term? Yes. What about 2 in for n? 2 squared? Yeah, that's 4. What about to the third power? 2 to the third power, that's 2 times 2 times 2. Yeah, that's 8. So that's the correct answer. Now, as we move on to a little bit more difficult of stuff, because this one's not really a pattern, but if you put this over 1, you can see that the denominator is changing. So sometimes our sequence is just defined as one number is staying the same over and over again, the 5 is in the numerator, and in the denominator is your common difference, your linear problem. And in this case, it's just 1n plus 0. If you want to write 1n plus 0, you could. But the first term is 1. The second term is 2 in the denominator. The third term is 3 in the denominator. So that's all we need there. Now, some questions are pretty tricky, if we're just alternating signs. But isn't it true, I'll change colors just to emphasize that you could talk about multiplying by the same number here. Times -1, times -1, times -1, times. So this is a common ratio type problem. And there's a couple ways around this answer. There's a lot of correct answers. Because I've seen some people just do -1 to the nth power. And this would work because -1 to the first power is -1. -1 when you square it. -1 times -1 is +1. But there are other correct answers. So let me circle this and then I'll kind of butcher it completely. You might, when we investigate this a little bit further, you might change your exponent to be n minus 1. Sounds weird right now, but now it's the wrong answer. Because if you did n minus 1 and you did your first term, you would get -1 to the 0 power, which is +1. Well, you can fix that by multiplying by -1, which right now might not make a whole lot of sense, but it might make more sense in the future. So I just want to introduce you to, there might be some shortcuts, some formulas that we'll be doing. Otherwise, most people leave their answer like that. All right, moving on to the next one. If you notice, there's a common difference there. You can try this on your own. Hit pause in the video. That common difference is 5. So I'm writing it like a linear problem. But if I plugged in 1 in for n, 5 times 1 is 5. So that's not correct there. Well, what can I add to 5 to get it to 10? You can add 5 to it. And now you can try the rest of the problems. If I plug 2 in for n, do I get 15, the second term? Yeah, 5 times 2 is 10 plus 5 is 15. So it does take a lot of practice. Now this next one, I just want to point out, because right now there's really no rhyme or reason. We'll learn more about this later. But there's definitely a pattern going on between 1, 4, 9, 16. This is not a geometric, it's not arithmetic. It's seeing that the second difference is the same, but some of you or somebody in this room, whoever's watching this, might recognize that these are perfect square numbers. We won't investigate too many of these, but at some point in this unit we will discuss square numbers. So it is true that 1 squared is 1, 2 squared is 4, 3 squared is 9. And when we come across that, we'll talk more about those types of patterns. And then just real quick, before moving too fast, the way we talk about these sequences is the n values must be integers. So when we talk about a sequence, in case you've forgotten what integers are, those are whole numbers, not... it's okay if we start with 0, but for the most part we want to start with 1. So maybe instead of saying integers, I talk about, how about positive integers? Now, depending on your teacher, some teachers start with n equals 0. Usually when that happens, they'll tell you. So as we look at this problem, I could see why somebody might say that this one's okay, because if you start at n equals 0, then this one would be okay. But for our purposes, we're going to start with only positive numbers. So n must be positive 1. So if I plug in 1 in for n, 2 times 1 is 2, plus 1 is 3, and we're looking at this point. And we skip over the decimal, so we don't want answers where we connect the dots. And that's why we want to go with option 3 on this. So hopefully I've explained enough and you will struggle a little bit through this assignment. Don't get me wrong. Feel free to come into class with questions. Notice the different notations and make sure you follow the directions, giving 4 terms when I ask for it, but notice the different notations that we have. And right now we're just sort of investigating these sequences. Whether we're talking about recursive definitions, we're getting you used to the sigma notation for sums. Feel free to write down any questions you have and then bring them back to class. And notice that on exercise 7, I am asking for a recursive definition there instead of number 6 where I'm asking for an algebraic, similar to what we did in the notes. There's Fibonacci again, so you'll practice that. And I really like a problem like number 9. These are good problems, and there's definitely a pattern going on. So I expect questions when you come back to class.